Hello everyone. Today's video is about the Core Practical 4, the first of the core practicals for the materials topic. Now, this is a deceptively simple core practical, and there is a large uncertainty consideration towards the end. So if you're very familiar with the core practical but are unsure about compounding uncertainties, scoot forward to the end where I will deal with one example of very straightforward uncertainty, and the second, what you have to do if you have to subtract quantities in uncertainties and the considerations that you need to put to that, because that is possible here and could be an advanced level question that goes with this. So what you've got here is you put a very large as you can, tube, hollow tube like this on a retort stand, and you're filling it with the liquid you want to measure the viscosity of. And you put rubber bands around the tube to mark the positions, because this is going to be where you're spotting the spheres as they pass through. I've drawn 3 spheres here. You can do as many as you like. Obviously, it's just limited by the diameter of the tube, what the spheres will actually fit down. And all you have to do then is take your sphere, drop your sphere in the top, and you are going to be timing the distance it takes the sphere to fall 2 distances. Now, before you begin doing this, there's a lot of measurements that you have to take in order that you can find the viscosity at the end, and I'll go through the equation that you need to use to do that. So first of all, we need the mass of the sphere, because we are going to end up calculating its volume and therefore its density. So we need the diameter of the sphere. Now be careful when you're asked what measurements you take, because obviously you don't measure the radius. We measure the diameter, and from that we just divide that by 2 to get the radius. But your measurement is the diameter, and that should always be on your table. You're then going to use the radius to calculate the volume of the sphere, which of course is 4/3 pi r cubed. From that you want the sphere's density, and I'm going to put a little subscript O here to stand for object. Obviously that is mass over volume. Try and keep everything in kilograms per meter cubed. It's just going to make your life easier. So when you measure the mass, the balance will give it to you in grams, just convert it straight away into kilograms. And the same with the diameter, just put it into meters, and then you don't have to worry about changing centimeters or millimeters cubed to meters cubed later on. The second thing you have to do is you need to find the density of the liquid. And of course, to do that, you need mass over volume again. Slightly easier here, you put your measuring cylinder on a top hand balance, zero the top hand balance, and pour in a known volume of the liquid, let's call it 100 milliliters. So you pour in your 100 milliliters and measure the mass of that 100 milliliters. Let's focus for a second on where we're supposed to put these rubber bands. This first rubber band here, you have to put it far enough down so that the sphere is already traveling at terminal velocity by the time it reaches it. So you might have to do some preliminary work. Now, how are you going to know? Well, the velocity between these 2 bands should be the same as the velocity between these 2. If it's not, then obviously the ball is speeding up as it goes down and hasn't hit terminal velocity yet. So you have to do a little bit of preliminary work to find out where it is you put the first band so that it's already traveling at terminal velocity. You then want to put the other 2 bands as far away as possible, because what we're going to be doing is measuring the time it takes to fall between these 2 sections using a stopwatch. And as I'm sure you're aware, you have reaction times. In order for your uncertainties to be as low as possible, you want to measure the longest possible time, so that any reaction time error has a minimal effect on your timing. And in order for the timing to be as long as possible, those distances have to be as great as possible. Now, obviously, there's a limit. It just depends on what size of tube you can get your hands on here. If you can manage to get an enormous tube that can reach almost down to the floor from the top of a bench, then absolutely brilliant. You can have them quite far apart, and you're going to reduce your uncertainties that way. So you can see here that we have quite a lot of measurements that we need to have. The mass of the ball, the diameter of the ball, the radius of the ball, the volume of the ball, the density of the ball, the mass of the liquid, the volume of the liquid, the density of the liquid. These 2 distances here, D1 and D2, which presumably will be fixed throughout the experiment. Then the time it takes to go between those distances, so T1 and T2, and we'd like to repeat that 3 times for each ball. When you're actually doing this experiment, of course, you're probably using washing up liquid or sunflower oil or something like that as your liquid. The ball falls down right to the bottom. You have to fish it out with a magnet. The whole thing is an absolute mess. So this practical actually takes quite a lot of time because of the preliminary experiments, because of all the measurements you have to make, and because you have to fish the ball out each time. So this is what your table might look like. I've put in provision for 4 spheres here. You're going to put in all the details of the spheres so that the goal is to find the density. But do remember, in any practical question in an exam, make sure that all the actual measured values are in the table. The measurements the person made. That is one of the faults with someone's table if they haven't put in their actual measurements. And then we have our 3 times it takes to fall distance 1, finding the average, and the 3 times it takes to fall distance 2 and finding the average, and we're going to use those averages then to find these velocities, the velocities for D1 and D2. What you'd like to use those for then is to find an average terminal velocity for each sphere. So we're making sure that we've taken averages of everything so that our terminal velocity can be as accurate as possible within the limits of this experiment. Other ways, remember that you do not want to introduce a parallax error in your timing, or you try and minimize it as much as possible. So you've got to make sure that when you are starting and stopping your timer or using the lap function on your timer, that you are actually at eye level with the rubber band. And for the same reason, you need to make sure that you are doing the same position for the ball. So it might be that you start and stop your timer when the bottom of the ball passes through the rubber band, or when the top of the ball passes through the rubber band, but just make sure you are consistent with that. And so that the distances you measure are the distances that the ball has actually fallen. The third thing you have to be careful of is that at no time during its fall does the ball get close to the wall of your tube, because that is going to cause drag effects with the wall. If you do that, you're going to introduce an error into your timing. You are going to measure a longer time than in reality the ball would take to fall. And that's then going to have a knock-on effect on all of your readings that you use that time for. So what are we going to use that for? Well, in a previous video, my video on fluids, I explained this equation that I'm about to write out here. You can go back and have a look at that to see where this comes from if this is entirely unfamiliar to you. The subscript O means object, so in this case it would be the sphere, and F means fluid. Eta is what we're trying to find, that is the viscosity of the fluid, and V here is the terminal velocity. So we want to rearrange this equation for eta. There are a couple of other ways that you could do this. You don't have to calculate the volume of the sphere at the very start, and you can substitute 4 over 3 pi r cubed in for volumes here. It doesn't really matter which road you go down. I think it's just simpler to keep it this way. So now for each sphere that you do, remembering that you'll have possibly a different density, but certainly a different volume for each sphere and a different radius, you should get a value of eta, which is the viscosity of the fluid. Presuming that you've used the same fluid throughout, you can then find the average to find an average value for eta. And this is where the uncertainties become a thing. So how do you estimate your uncertainty in eta? Method number 1, and by far the easiest one, is to simply look at the range that you got for your etas for each of your spheres, and even better if you've got multiple spheres here, and find half the range. That will give you your absolute uncertainty in eta. You can then divide it by your average value, multiplied by 100 to get a percentage. Very straightforward. Not so straightforward is using your actual measured repeat data to find the uncertainty in your eta. And again, you can go relatively easy with this, or you can go the whole hog and really get yourself involved in compounding uncertainty. So I'm going to do both versions here. If you think it's never going to happen, I'm never going to have to compound the uncertainties to that extent, then you can just scoot through the last part of the video, because I may be spending some time showing you exactly how to compound all of the uncertainties that you have in your measurements here. Option 2 is to use half the range of your timing over your average t, multiply by 100, and get your percentage uncertainty in each of your times. You could be justified in ignoring the uncertainties in all others. After all, to find the diameter, you use a micrometer screw gauge, and we know that the micrometer screw gauge has a very high resolution, and even if you took repeats of the diameter, the chances of you getting much of a range in that diameter are slim, so you could ignore that, and that would be justified. You could also, depending on the balance that you used and the actual mass of your sphere, probably ignore the resolution of the balance. So it might be to 0.01 grams, at which point, if you've got a ball of 10 grams, that means that that uncertainty is as good as negligible and can be ignored. Which means that both the mass and the volume uncertainties could be ignored, even though your percentage uncertainty in your diameter would be tripled to find your volume. If it's down in the 0.1%, then tripling it isn't really that much of a big deal. So mass and volume could be ignored, which means your density could be ignored. If we look back up at the equation, let's see what else goes into viscosity. So we're ignoring densities here, saying that the uncertainty is negligible. Again, our volume uncertainty we've said is negligible. Our radius uncertainty is negligible. And here, our uncertainty in our terminal velocity, if we can also assume that our uncertainty in our meter rule is negligible, which for small distances might be a little bit of a stretch, then we would say that the uncertainty in our terminal velocity is the same percentage uncertainty in our timing. That means if you ignore all the uncertainties in all other measurements, the percentage uncertainty in your timing is the same as the percentage uncertainty in your viscosity. However, suppose you think, I can't really ignore all of those uncertainties. Or suppose you get a question where it tells you to ignore certain uncertainties but not others. You need to know what you do on the occasion where you have to compound every single one. And so I'm going to go through and show you how to calculate all of the uncertainties in these, how many of them there are, and what you do when you have to add them all together. And it's useful to keep the equation right next to you here, because of course anything that went into that equation is going to contribute to the uncertainty in your viscosity, and so we got to keep an eye on it. Okay, let's start with our velocity. That one is straightforward. We've already mentioned that. It is the percentage uncertainty in the time plus the percentage uncertainty in the distance. So let me show you how to do that. That's how you get your uncertainty in the times. Because it's distance divided by time, we have to add the percentage uncertainty from time to the percentage uncertainty from the distance measurement. So we've added together percentage uncertainty in time and percentage uncertainty in distance to give us the percentage uncertainty in our terminal velocity. All right, that's the first one. Radius. There's our second one. Now, depending on whether you took repeats of your diameter reading, and remember, because it's the diameter we measured, it's half the resolution of the micrometer over the measurement of the diameter, not over the radius. Times 100, that will give you the percentage uncertainty in diameter, and the radius will have the same percentage uncertainty. You can add these as you go along, because for each of these, we are going to be adding their percentage uncertainty together. So anything that's multiplied or divided, you add their percentage uncertainties. So the total of that, 6 pi obviously doesn't have an uncertainty, g doesn't have an uncertainty, so now we need to look at volume. And because the volume is calculated from 4/3 pi r cubed, anytime you cube it, you have to multiply the percentage uncertainty in the radius by that power, anytime, any power. So that this time it's 3, so we end up with our percentage uncertainty in volume, and again, you could start adding all of those together already. Finally, we have our densities. Now these densities are subtracted, and they're both calculated values, which makes this quite tricky, and Edexcel don't actually have a method for compounding uncertainties that are subtracted when it's a calculated value rather than a measured value. If you're subtracting two measured values, 2 points along a ruler that you measure, and you're subtracting them to find the distance between those points, you would take half the resolution of the instrument, as usual, and you put it over the difference between the two. So the value you actually want times 100. With this, the best way is to use an average of the uncertainties of both of these. So first of all, we have to find the uncertainties in, let's say, the density of the object. First of all, uncertainty in mass. Which is half the resolution of the balance over the measurement times 100, and then you've got to add that to the uncertainty in volume, which we have up here. For the density of the liquid, that is going to be the percentage uncertainty in the volume of the liquid. You've got to add that to the percentage uncertainty in the mass, which would be calculated the same way as that for the density of the object. So what do you do now? Like I said, Edexcel don't have actual guidelines for calculated values like this. Anytime we subtract quantities, we tend to use the absolute uncertainties because those uncertainties will be in the same unit. So what we really need is to convert these percentage uncertainties into absolute uncertainties. And here's where it's a matter of opinion. You could take the best or the smallest uncertainty in that. You could take the greatest uncertainty, depending on whether the object or the fluid had the greater uncertainty in kilograms per meter cubed, or you could take the average. For me, taking the average is the most sensible one. Find the average of those two. And remember, we're talking about absolute uncertainties here. To find the percentage uncertainty in this quantity mu O minus mu F, we need to take this average U that we had up here, put it over whatever value of mu O minus mu F, whatever that is, times 100, and then we will have a percentage uncertainty for this quantity here. Once you have that, you then have to add that percentage uncertainty to all of our others that we got above. And let's have a look and see. We have 1, 2, 3, and now 4 percentage uncertainties that all have to be added together to give you your total uncertainty in the viscosity. Now that is if you're being very picky. That is if you're told that you've got to use the uncertainty in all of your measured data to find the uncertainty. Personally, I think this would be too many marks. It would have to be more than 6 marks for the amount of work that is going into doing that. So what's more likely is you'd be told to ignore the uncertainty in perhaps everything but the time and the distance measured, which means that your uncertainty in viscosity would be the same as the uncertainty in terminal velocity. That's a reasonable level of ignoring uncertainties because all of the other instruments are likely to yield quite small percentage uncertainties. It has become more common, however, for them to ask you about quantities that are subtracted. So make sure that you know you have to find the absolute uncertainty in each quantity, or in the quantity being measured, and put that over the subtracted value. What the effect is, of course, because you're putting it over a smaller value than what you might have measured, is that your uncertainty for quantities that are subtracted is greater. The last thing I want to mention before I go is Edexcel and its love of how could you use technology. You can't use light gates for this, obviously, because you're putting rubber bands around the tube. And you can't have the light beam penetrating the rubber band, even if it could start and stop where the ball was going through, even if you could guarantee that the sphere was going to break the light beam at the same point each time, you still couldn't use it with the rubber band. So it's just not possible here. The only thing you can do to decrease the percentage uncertainty significantly is try and have the greatest possible distance between the bands.